Alrighty guys, this is electron orbital diagrams, electron configurations, and Lewis dot diagrams practice problems. Alright guys, if you have not yet gotten your periodic table of elements out, you need to get it out right now because it is going to be necessary for doing these. So the very first orbital diagram we're going to do is for hydrogen. So the first thing you have to do is find hydrogen on your periodic table. Hydrogen is your very first element, and we're going to ask ourselves, how many electrons does hydrogen have? Because this whole thing is about graphing and representing the amount of electrons your element has. So you go to your top left corner, and you're going to see your atomic number. The atomic number for hydrogen is 1. So the atomic number, 1, represents the number of protons an element has. But in a neutral atom, you can assume that the atom will have the same number as protons as electrons. That's why it's neutral, because the two charges cancel each other out. And so we're going to say it has 1 electron, and based on the Aufbau principle for this orbital diagram, we're going to start at the very lowest energy level, at the 1s energy level. We're going to draw half of an arrow facing up, and that represents 1 electron in the 1s orbital. So what that's saying is for hydrogen, we have it, there's 1 electron in this energy level that's closest to the nucleus. It's going to be anywhere inside of a ball-like configuration. So it can orbit, the electron's going to orbit that nucleus somehow, anywhere within, most likely, this ball-like orientation. So the ball is not the electrons, it's just saying that electron will orbit in this ball-like pattern. It's a highly likelihood of it being there. And so what you need to ask yourself about the periodic table of elements is, why is it shaped the way it is? Well, it's shaped this way instead of just like one long list listing protons, going from the lowest amount of protons to the highest number of protons, starting with hydrogen, ending all the way over here with magnesium. The reason it's not in a list is because it's blocked in a specific way to show you about the electrons, to talk about the electrons. It's showing you this S block, this D block, this P block, and F block. So if you're using the Zastic periodic table, which I think is just fantastic because it has all these pretty cool just like keys to try to figure out the periodic table on it, you'll notice that this group right here is going to represent your S block. Group 1 and group 2 will always be in your S block. So meaning the electrons, you're going to have up to 2 electrons in your S block, and they're always going to orbit around the nucleus in a ball-like pattern. Over here is going to be your P block, because you can see it down here, it says P, except helium. Helium is over in your S block. You'll just have to mentally move it over. Your P block is those dumbbell-shaped patterns. So the electrons are orbiting around your nucleus in dumbbell-shaped patterns. Then you have your D block over here, which you have more of like your clover patterns. And then your F block, which has the crazy flower-like patterns. And so as you move down your periodic table, you're moving, you're going to different energy levels. So these periods, period 1 is saying you are at the lowest energy level. You are at the energy level closest to the nucleus. The electron is closest to the nucleus at 1. And then energy level 2, you're slightly farther from the nucleus, and you can have your S block. And if you moved your finger over, you could have your P block. And if you move to 3, period 3, you are going to be able to do S block, move your finger over P block, and then 4, S block, and now you're hitting D block, and then P block. So do you see what I'm saying? The periodic table, the structure is extremely important, and it's like this huge cheat sheet. You just have to know how to use it. So I know that was long, but it'll be very useful as we carry on. So our electron configuration, we're going to write it out. So our electron configuration, if we're looking at our orbital diagram, is just your first quantum number, your energy level, your principal energy level, which is 1. And it's asking about the subshell you're in, the orbital that, it's talking about that ball shape. So that's S. And then it's asking, okay, well, how many electrons do you have? You'd say 1 as a superscript. So your electron configuration for hydrogen would be 1s1. And hydrogen does not have a noble gas electron configuration. And we know this because hydrogen is the very first element. And the next element is our noble gas helium. This whole group right here is our noble gases. So to have a noble gas electron configuration, you actually have to have a noble gas come before the element. So hydrogen, it doesn't have one. So we can just write N A, not applicable. And that is our first orbital diagram and electron configuration. Now we have beryllium. So same thing, guys. We need to find beryllium on our periodic table. So beryllium is right here, and we find the atomic number in our top left corner is 4. So this is going to tell us how many protons we have in the element, and the protons correspond to the number of electrons you have in a neutral atom. So if there's 4, we're going to go 1, and then 2. Aufbau principle, we have filled up the lowest energy level. Each of these orbitals, they can only have 2 electrons per orientation. And S's can only have 1 orientation, meaning S is shaped like a ball. If you move that ball in any kind of orientation, it's always just going to look like a ball. Like you can't, it can only be 1. So that's 2, and we're going to do 3, 4. So we're representing the electrons, their spins going, clockwise and counterclockwise. That's why it's going, one is going up and one is going down. These electrons are occupying the same orbital, but they're repelling each other, they're negatively charged, and so they're going to have opposite spins. They're going to want to spin away from each other. They're trying to kind of get as much space as possible. And obviously I'm personifying here. Electrons don't try. It's just based on their charges, but it's a way to explain it. So electron configuration. If we were to write out our electron configuration, we would write it like this. Looking at our orbital diagram, we have 1, S, and we write a superscript 2, because we're saying we're at 1 energy level, we're at the S subshell, and there's 2 electrons. So it's totally filled up, and we move to our next energy level. So that's going to be 2S2. Again, that S is totally filled up, and we have 4 electrons, and that is it for our electron configuration for beryllium. Now, if you did not have an orbital diagram and you were just doing this based on having your periodic table, you could find beryllium on your periodic table, which is great, and you start at the beginning. You say, okay, at the very beginning, we have our period 1, so that represents our energy level, our principal energy level, so that's 1, and then right here, 1, 2, if we picture helium over here, there's like 2 blocks, 2 groups, and it's going to be, a max of 2 in your subshell. So 2 electrons, sorry. So you have 1 S, because it's in our S block, and then 2 electrons. 1 S2, if we were just counting the blocks we have. And then that's it. That's it. Like the helium's over here. There's no P block in the first energy level. So then we move down. We're at our second energy level. Our second energy level would be 2, so we write 2. We're in the S block. Remember, if you forget, this is showing you, this is your S block. These first 2 groups, 2 groups are your S block. And so that's 2S, 1, 2, 2S2. So don't mistake it as like I'm counting the actual elements. Like I'm not. I'm just counting the places, like the blocks, so to speak. But it's just because that's how brilliant people have designed this periodic table, so that you can count these spaces, and that will tell you the number of electrons and the energy level of those electrons and the shape, the subshell that those electrons are most likely going to be found in. It's brilliant. It's like absolutely brilliant that they were able to do this. It's amazing, honestly. So yeah, this thing, it's awesome. You should love it. You should like whisper to it each night that you love it and you just want to be friends forever. All right, noble gas electron configuration. This does have a noble gas electron configuration because helium came before beryllium. So we're going to go to helium and we're going to write helium. So you put a bracket and then you write your noble gas. So that's helium. And then your noble gas kind of takes off that first row right here. And then we start right at our energy level, our 2, our second period. So that's going to be 2s2. So you're asking yourself, why did I just do that? That did not save me a lick of time. And it didn't. But it will when we get to later elements. So like elements down here, the noble gas electron configuration is just, really helpful. All right, now we are on to carbon. So first step, we find carbon on our periodic table. So carbon is right here. It's super important. It makes up, all living life, carbon. And carbon has an atomic number of 6, which means it has 6 protons. And because it's a neutral atom with 6 protons, you can assume it also has 6 electrons. So, Aufbau principle, we start at our bottom. And your Pauli exclusion principle shows that each electron is going to have opposite spins. So we draw one up, one down. So that's 2. And then we move to our next highest energy level, so which is 2s. That's 2 more electrons, so 2, 4. And now we are working with 5, and then 6. So the question is, why did I not just put in another arrow right here? Why didn't I do that? I'm going to erase that just to make sure you guys don't get confused. It is because of your Hund's rule. So Hund's rule says that electrons, if there is an orbital available, the electrons are going to fill in those orbitals before they press together and fill in the same orbital. And so a way you can think about this is imagine a bunch of strangers who don't know each other at all getting onto a bus. Now, if these strangers are, socially normal, they're probably going to sit in their own seats before they choose to double up. It's just kind of how it works. They want their own space. And so in the same way, you can think of electrons. If there is space available, they're going to spread out. And so each of these is representing, a different orientation that those dumbbells can be in. And that is in your, your second energy level and in your P subshell. So our electron configuration for carbon, and we can write it, we'll write it first from just looking at our orbital diagram, would be 1, energy level 1, subshell S, it's that ball-like shape, and we have 2 electrons. And then we have our next energy level, which is 2s, and then 2 more electrons. And then we are on to 2 same energy level, but our new subshell, our P subshell, 2p2. And if we did not have our orbital diagram and we just had our periodic table of elements, which is the best thing ever, we could solve it, no problem. We find carbon on our periodic table, and we say, all right, let's start at the beginning. Our very first period right here is 1. So our lowest energy level is 1. So it's 1, and then we're in our S block, so it'd be 1s, and then there's 2 spots right here. There's 2 blocks, and we'd say that's 1s, 2. It could have a max of 2 electrons there. 1s2, then we move down, and we are in our second energy level. So that's 2, we're in our S block, 2s, and there's 2 blocks, 2. And we haven't hit carbon yet, so we're just going to keep on moving across our periodic table. We're going to drag our finger over, and now we are in our P block, but we are still in our second row. We're still going to count. So that's 2p, because we're in our P block, 1, 2, 2p2, and we've reached carbon. And so that gets us all 6 of our electrons, and it tells us exactly where those electrons, well, most likely where those electrons are going to be. They're going to be at the lowest energy level in an S subshell, and there'll be 2 of them. Then the next energy level, 2, in the S subshell, there'll be 2 of them. And then the same energy level, but in the P subshell with 2 electrons. So your noble gas configuration for carbon is we're going to come to our first noble gas that we passed on our way to get to carbon, which is helium. So you write it in brackets. That was kind of a rough looking bracket. So we have helium, close bracket, and then it's going to be our energy level that immediately follows helium. So that would be 2s2, if I can draw that 2, and then 2p2. And that is your noble gas electron configuration for carbon. And again, doesn't save us a lick of time, but it will. Further elements. So it's just good to practice. All right, nitrogen. We have nitrogen. So again, this should be becoming a routine. You find nitrogen on your periodic table. Nitrogen is right next to carbon, and we're thankful for our nitrogen for many reasons. Helps us live. Nitrogen has 7 protons. Its atomic number, remember, atomic number stands for the number of protons it has. It has 7 protons, but because it's neutral, we can say it also has 7 electrons. So we're going to fill in our orbital diagram to get us to 7 electrons. Aufbau principle, we start at the lowest energy level and we work our way on up. We're going to show these opposite spins of these electrons, showing 1 arrow up, 1 arrow down. We get to our P. So we have 2, 4, 5, 6, and 7. And that is our electron our orbital diagram, for nitrogen. So looking at our orbital diagram, we can draw our electron configuration. So that's 1, S, 2, 2s, 2, finally 2p3. And if we did not have our orbital diagram and we are just looking at our periodic table, we find nitrogen. So we're like, all right, let's back it up. Let's start at the beginning. So we have 1 S block, 1, 2, 1 S2, move down, 2 S block, 1, 2, 2, move our finger over, 2 P block, 1, 2, 3, 2p3. Boom, we got it. Our noble gas electron configuration, just like carbon before, it passed. Oh, that bracket got crazy. Sorry, guys. We passed neon. That was the noble gas that we passed. Passing gas. Oh, man. Oh, I cracked myself up. All right, so that's neon. And then we had 2s. I'm still laughing at that. I'm like a child. 2s2, 2p3. Again, didn't save any time. Why are we doing it? It's just good practice. Magnesium. All right, let's check out magnesium. First thing you got to ask yourself is, where's magnesium at? So magnesium, it's a metal. It's right over yonder in group 2. So, and it's in our 3rd energy level. That's exciting. That's something new. We haven't been to our 3rd energy level yet, so you should be like, oh, 3rd energy level. I'm kind of assuming no one is watching this, so I can make this however I want. All right, so magnesium, it has 12 protons because its atomic number is 12. It's a neutral atom, so we can say it has 12 electrons, and we're going to fill this guy up, starting with 1, 2. 1s is all full up. 2, so that's 2, so that's 4. We have 5, 6, and 7. Now we come back, we double up because it has to, kind of like the strangers on the bus. Now they have to double up, so that's 8, 9, 10, and then We have 2 more electrons we need to write in, so we move on to our next energy level, 11, 12. And that is our full 12 electrons. If we were to write our electron configuration, we just look at our orbital diagram. We start at 1, S, 2, looking a little bit silly there, and then 2, S, 2, we're just going from lowest to highest. You have 2, P, 6, and now our second energy level is all full up. It's both S and P block are full up, so we move into our third energy level. So that's 3, S, 2. And that is our electron configuration for magnesium. If you did not have your orbital diagram and you're just looking at your periodic table, you find magnesium and then you work your way backwards. You start at the beginning. We're going to work towards magnesium. So we go period 1. We have 1, 2, so it's 1, S, because we're in our S block, and we have 2 spots, so that's 2 electrons, 1, 2, 1, S, 2, and we move down to our second energy level, which is at 2, and we're in our S block, so it'd be 2, S, 1, 2, 2, S, 2. We've used our finger, we just follow it on over, and we hit our P block, and that's 2, because we're in our second row, 2, P, 1, 2, 3, 4, 5, 6, 2p6, and we still haven't hit magnesium yet, so we need to come back and start over here on our third row, and that's 3s block, so 3s 1 2. That hits magnesium, so 3s2, and that would be your full electron configuration. So your noble gas electron configuration. Finally, this is going to save us a little bit of time here. We hit neon, was our last noble gas before we get to magnesium. So neon, we're going to write over here as an N, E, neon. And then we just go straight to our next energy level after neon, which is 3, S block 2, 3s2. And see, it did save us time, which is nice. All right, sulfur. We need to find sulfur on our periodic table. So sulfur is right over here. It's a non-metal and it's very stinky when it, is gaseous. Man, making all kinds of gas jokes. But for real, sulfur really does stink. Okay, so sulfur has an atomic number of 16, which is meaning it has 16 protons, but because it is neutral, it has 16 electrons, and so we're just gonna keep doing our thing. We're gonna start at the lowest energy level, and we're gonna work our way on up to get to that 16 electrons. So that is 2, 4, 5, 6, 7, 8, 9, 10. And we have 11, 12, 13, 14, 15, and then finally 16. And that gets us to sulfur. So our electron configuration, if we were to write it out looking at our orbital diagram, is going to be 1s2, 2s2, 2p6, interesting 6, 3s, oh my goodness, I can't do it. There you go, 3s2, and then 3p4. All right, again, if we did not have our orbital diagram and we are just looking at the periodic table, we can start by finding sulfur on the periodic table, and we work our way from the beginning all the way to sulfur. So we have, starting at the beginning, 1, row 1, S block, 1, 2, 1s2. All done, we move to our second energy level, 2, S block, 2, so 2s2. Use your finger, follow all the way to the P block, that'd be 2, and then 1, we're in our p block, so 2p, and then 1, 2, 3, 4, 5, 6, 2p6, and we're moving down to our third energy level. So we have 3 s block, 1, 2, so 3s2. Use our finger, follow it on over. We're at 3p, 1, 2, 3, 4, 3p4. I'll be darned. Look at that. It gets you exactly what you need. Without the orbital diagram, you can have your periodic table, and it's splendid. All right, so your noble gas electron configuration, we look for the noble gas that came just before sulfur, so in the row before it, and that would be, sorry, I don't know if you could see that, that would be neon. So we write a bracket, and then we write neon, and we close the bracket, and we move to our next row, our next period, and that would be 3, so our third energy level, 3s2, and then 3p4, and that does save us some time, which is nice. And that is your electron configurations for sulfur. All right, argon. Argon, we're going to do our first noble gas, argon. So argon is over here, and it has 18 as its atomic number, which stands for 18 protons. Remember that. That's what that number actually stands for. But it's a neutral, it's a neutral atom, and so we're going to say it also has 18 electrons. That way it doesn't have a charge. So we have 1, 2, 3, 4, 5, you mateys, and 6, 7, 8, 9, 10. You're like, are you gonna stop with the accents? Maybe, maybe not. It's my video. I can do accents if I want to. But now I've lost track. So that's 12, 13, 14, 15, 16, 17, 18. Woohoo! Aren't you celebrating? Aren't you amazed? That was 18 electrons. Well done. You should pat yourself on the back. So, the interesting thing about noble gases, the reason they're called noble gases, is because they do not react. Like, they don't react with anything. And that is because they have a full octet, meaning they have a full 8 electrons in their outermost shell, and they are just living their best life. They are living the dream. And so you can actually see that right here. So your third energy level, you could not put any more electrons in there if you tried. You just can't. It's all filled up. 2, 4, 6, 8. They have 8, and they're happy. And so that's just important to know for later. That's like actually really important. And you can visually see it on this diagram. So our electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. And that is your electron configuration for argon. If you did not have an orbital diagram and you're just doing it from your periodic table, you find argon, which is down here. You start at the beginning, you'd say 1 s block, 1, 2, 1 s2, all done. 2 s block, 1, 2, 2 s2. Move your finger over. You get 2p, 1, 2, 3, 4, 5, 6, 2p6. All done. Move down. We have 3 s block, 2, 1, 2, and then 3s2, and then we move over. We have 3p, 1, 2, 3, 4, 5, 6, 3p6. And that would be all of them. So your noble gas electron configuration, it'd be great if you could just write, brackets, argon. But that's not how it works. You have to go to the noble gas that was right before the element. So it's still going to be neon. and then you write your electron configuration in the following neon. So neon was the very last element in row 2 in your second energy level. So now you go to the third. So 3s2, 3p6. And that is your noble gas configuration for argon. Okay. Wow. Titanium. This is when things in chemistry get exciting. I know you're already like just amazed. Just throwing your hat off like, wow, I wish I could do this all the time. Well, guess what? You can. And you can look up practice problems all you want. Okay, titanium. We're going to find titanium on our periodic table. And the reason why I'm so excited about this is because titanium shows up in our D block. We have yet to do anything in our D block. D block is like a little bit funky, so it's very fun to get to D. So we're going to look at our atomic number, 22, and that represents the number of protons, not unicorns. I know someone was thinking it. Unfortunately, not unicorns, but we can't see atoms. Anyway, not a conspiracy theorist. Let's fill in. Our protons correspond to the number of electrons in a neutral atom. So it's going to be 22 of them. So we've got to draw 22 of these little arrows. Each arrow represents an electron that's being filled in from our lowest energy level to a higher energy level. And the reason why our electrons start at these lower energy levels is because electrons are negative, our nucleus is positive, and so nucleus is going to be pulling these electrons towards itself. And so it wouldn't make any sense for these electrons to be way out yonder when there's this force literally pulling them towards the nucleus. So just kind of like a logical thought there. But okay, moving into our D. So I kind of lost track. I think we need 2 more electrons there because that was 20. 1, 2. Cool. You're like, all right, you like really built that up and that wasn't very exciting. Well, buckle up because it's about to get more exciting. When we write our electron configuration, I think what you really need to pay attention to is in our D block. Did you notice there's a 3D and a 4S, and we filled in that 4S before the 3D. It's just like, wait, what's going on here? So if you recall, when we were talking about our principal quantum number, our first quantum number, our energy level, the shell that it's in, it is going to, these transition metals are not going to follow the 1, 2, 3, 4, 5, 6, 7 rule. They're going to follow that rule -1. So this D block right here is technically, it's in this 4th period, this 4th row, but the rule is you say it's 4 minus 1. So the energy level is actually 3, not 4. And you may be asking yourself, well, why don't we just put it in the 3rd one? Well, guys, chemistry is complicated. And so in order for this tool, in order for you to continue to list your elements going from the number of protons going from least to greatest, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, their atomic number increasing, you couldn't just throw this up here because there are 21 protons here and there's 12 protons of magnesium. Like, you can't just put those next to each other. And so they lowered it, but they gave you a rule so you can remember, like, okay, this is still technically your 3rd energy level where your electrons are in the D block. And if you want it to be simple, like, too bad, because this represents nature, and nature is not simple. It's like extremely complex, which is really good news for us because that means, we can live. So our electron configuration, it's going to be 1s2, 2s2, we just write lowest to highest, 2p6, and then 3s2, 3p6. 6. And this is the part you have to watch. It has to continue to go from lowest to highest. So even in your orbital diagram, even though you filled out the 3D last, what you need to do is write in 3D2, because it's still part of that third energy level, 3D2, and then you end it with 4S2. Now this actually shows you why when you are working with valence electrons, we don't talk about this whole section right here. And that's because these electrons are not on the outside. It's always going to be in this 4s, or not 4s. It's always either going to be S or P is going to be on the outside. D and F actually get shielded by S and P. So that's why, again, valence electrons, we're only going to look at, the S and the P blocks. Just an important note. It's just kind of, cool that you can see it from there. So we're going to ask ourselves, what is a noble gas electron configuration? And, titanium is right here. So we go to the last noble gas we passed, which is argon. Still saying noble gas we passed. Last noble gas and the energy level right before it. I don't really know how to say that other way. Okay, so that's argon. And then we're going to say argon, and that's 3D2, showing kind of where the titanium is, 3D2, and then 4S2. And that would be your noble gas electron configuration for titanium. So it's saying, hey, you've got all the configuration up to argon, and then when we hit titanium, we hit 4S2 and 3D2. And even if, guys, you didn't have your orbital diagram to go off of and you're just having your periodic table, which I think is, fantastic, just remember you write your numbers going from smallest to greatest. So even if you wrote down 4S2 and then 3D2, you would just need to, erase that and switch the numbers. So it will always go from your lowest energy level to your highest energy level when you write it down. I hope that helps. Okay, iron. So this is going to be our last example. And again, iron is in the D block. I think the D block is a little more tricky. So we have 2 examples with iron. And so the first thing we're going to do is we're going to find its atomic number, which is 26. 26 is the number of protons that iron has. And a neutral atom is the same as the number of electrons. So we are going to fill in 26 electrons for iron. Iron is incredibly important. Makes up lots of metals we use, mixed with other metals to make alloys. Pretty awesome that iron exists. And this is a bit of a slow process on a computer. Thus, while I am rambling about iron, we're moving on. We're almost there. Okay, so that's 20, 21, 22, 23, 24. Oh, these arrows are looking rough. These half arrows. 25, 26. Make sure that's, just making sure I counted right. 26. Great. So our electron configuration, if we were looking at our orbital diagram, is going to be 1s2, 2s2, 2p6, 3s2. We have 3p6, 4. Oh no, you can't write a 4. There's still a 3 out there. All right, let's fix that. I just wasn't even paying attention. I was just writing it, see? You gotta do 3d6. That's a really big superscript. 3d6. And then, last but not least, 4s2. Man, I promise my writing looks better in person, but not by much, not by much. I can't necessarily blame PowerPoint. All right. If we did not have our orbital diagram, we can look on our periodic chart. We can find iron on it, iron, Fe. Those two things don't sound anything alike, but what ifs. I believe Fe stands for ferrin, and I believe it's Latin. Might be wrong, so feel free to correct me. So iron is right here, and we'll start at the beginning, and so we have 1s12, 1s2, 2s12, 2s2. We use our finger, follow it over, 2p, 1, 2, 3, 4, 5, 6, 2p6, move down, 3s12, 3s2, follow our finger over, 3p, 1, 2, 3, 4, 5, 6, 3p6, moving on down, and then we have 4s2, 1, 2, and then, because this is the D block, we go back saying it's 3, because it's 4 minus 1, 3d, 1, 2, 3, 4, 5, 6, 3d6, and we'll just have to remember to switch the 3d and the 4s2 when you write it down, so that the 3s stay with the 3s, and then the 4 follows. So you always are writing from your lowest energy level to your highest energy level. And so our noble gas electron configuration, we find the noble gas configuration, or the noble gas that is in our period right before we hit iron. So that would be argon. So we write down here, argon. And then we jump to the next period. So that would be 3d6 followed by 4s, oh dear, there you go, 4s2. And that would be our noble gas configuration for iron. All right, we are moving into our Lewis dot diagrams. Now, this concept of Lewis dot diagrams is extremely important to grasp for like the rest of this course and just understanding chemistry. So Lewis dot diagrams are going to represent our valence electrons. Remember, I briefly talked about our valence electrons. It's going to be the electrons that are in the outermost shell, the outermost energy level. So these are the ones that are going to be interacting and doing chemical bonds. So our valence electrons, because D and F are actually shielded by S and P blocks, we're not going to look at our transition metals in our D block or our let's try this one more time. Our lanthanides or actinides, sorry, it took me a while to say that, at all. So our valence electrons, they're going to go by group. So group 1 is all going to have one valence electron. 1. For all of these in group 1, it's going to have one valence electron. And then when you move over, group 2 is going to have 2 valence electrons. They will always have 2 valence electrons, your outermost electrons. So we're not counting all the electrons that these atoms have. We're just saying how many electrons are on its outermost shell. It'll always have 2. We come over here to our P block, and these will always have 3 valence electrons. It's going to be 1, 2, 3. 3 valence electrons, and then we have 4 valence electrons, 5, 6, 7, and then 8. Our noble gases will always have 8 valence electrons. That is why they're so noble. They are all full up, and they do not react with anything because they need no electrons, and they don't want to lose any electrons. They just don't do much. Okay, so neon. We find neon, and we find what is its group. So it's in 18, and so we just, some periodic tables actually have 1A, 2A, 3A, 4A, like they're actually showing you like the numbers for the valence electrons. Your Zastic periodic table does not show that, but you can just subtract 10 from this side, or just, remember it. So neon, right here, it's going to have 8 valence electrons. So our Lewis dot diagram is just going to show our electrons, and we're going to represent them by dots. Don't know if you caught that from the title, a Lewis dot diagram. And so what I'm doing right now is every time we represent electrons, we're trying to, represent reality. And electrons are not going to want to be right next to each other because they're all negatively charged, and so they're going to repel each other. So we're showing them as being spread out. So I start at the top, I go 1, 2, and then right, left, 1, 2, 3, 4. Now there's 4 more electrons that need to be drawn. So that would be 5, 6, 7, 8. And that neon is all full up. It has 8 valence electrons. Every electron has its pair. It's completely done. So argon is next. Hint, argon is also a noble gas, and it's going to have 8 valence electrons. Anything in this group right here is going to have 8 valence electrons. So again, we're going to draw 8 valence electrons. That's 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons. Krypton and xenon. I'll blow the surprise for you. Krypton and xenon, those last two, are also noble gases. So they're all going to have 8. So no surprise here. We're going to draw 8 dots around krypton. 6, 7, 8. Ooh, this dot is like a little small. So there's 8 valence electrons there. Sorry, some of the dots are like kind of small. And then xenon, again, it has 8. And it's not that it only has 8 electrons, obviously. It's that it has 8 outermost electrons. So its S block and its P block are all full up, showing 8 electrons, because S can have up to 2 electrons, P can have up to 6 electrons because it can have 3 different orientations. And now you have completed your Lewis dot diagrams for these noble gases. So beryllium, we need to find where beryllium is on there. So beryllium is in group 2. Group 2 will always have 2 valence electrons. And so we write 2 valence electrons around beryllium, and we're good. Chlorine, let's find good old chlorine here. Chlorine is over here. So chlorine is right next to the noble gases. It has 7 valence electrons because it's in group 17. We subtract 10, and that's 7. So we're going to draw 7 electrons around chlorine. Now, what you should know is that atoms really, really, really want to have 8 electrons because then they're all full up. They don't need any other electrons in their outermost shell. And so this specific group right here, group 7, or 17, but for 7 valence electrons, this group is called the halogens, and they are extremely reactive because they're going to just yank an electron off of something else because they just need 1 more electron to get to that 8. And again, it's not that electrons and atoms want things. It's just the way charges work. All right? So then you have fluorine. Again, fluorine is in that halogen group. It's in that 7th valence electron group. It's 17. Take away 10. So we're going to say 1, 2, 3, 4, 5, 6, 7. Again, extremely reactive. Sulfur, our kind of more stinky one, is over here. It's in the 16th group, so it's going to have 6 valence electrons. So sulfur, we're going to write with 6. So that's 1, 2, 3, 4, 5, 6. So sulfur has 6. Very last slide, our very last Lewis dot structures. We're looking at iodine. Iodine, it is right here, and it is sorry if you can't see that, iodine's right here, and it is a halogen. It's in that 7 valence electrons, our 17th group right here. So we're going to draw 7 outermost electrons here. So that's 1, 2, 3, 4, 5, 6, 7. So that's 7, super reactive. It's really going to want to rip away an electron from something else. And then we have oxygen. it's over right here. Oxygen, it's in our 16th group, and so that means it's going to have 6 valence electrons, because I took away 10 in my head. So that's 1, 2, 3, 4, 5, 6. 6 valence electrons. Lithium. Lithium is right over here. Lithium is in group 1, so it's going to have 1 valence electron. Now, because lithium only has 1 valence electron, in order for lithium to have a full outer shell, it could just get rid of one of its electrons, and then, you know, it would be charged, but it would then have a full outer shell, which atoms really like that. They like having this nice full outer shell. So lithium wants to get its electron taken, and, you know, iodine wants to take its electron. So it's just, you know, for future reference, kind of interesting, good to think about. Okay, our last but not least is potassium. It's not potassium, it's potassium. There's no K in it, and I'm not entirely sure why it's a K. I forget. I'm sure it's something with some sort of language and some sort of name. But, you know, K, potassium. And it's going to be in group 1, and it has 1 electron. Again, it's going to want to lose that electron. So, and when we talk about bonding, elements that are like in group 1 and 2, they're going to want to lose those electrons, because that's the quickest way to get a full outer shell. But that will be another conversation for another day. And this concludes our practice problems. So, good work, guys.